In 1982, in the Lancashire town of Blackburn, a massive industrial glass furnace was allowed to go cold. It was not a quiet shutdown. It was the end of a national nervous system. This factory floor had produced millions of glass electronic valves. They were the glowing hearts of almost every wireless set in Britain. The colossal machinery was dismantled. The British workforce was sent home. A decade earlier, that same name had meant precisely the opposite. The Mullard badge was a guarantee of reception. It was displayed in high-street electrical shops. It was stamped on the glass inside the cabinet. But the real story of Mullard in Britain is not merely the closure of a northern factory. It is the story of how an entire nation's listening culture became dependent on fragile glass envelopes. It is the story of the local repair bench, and it is what happens when the market decides that a trusted component is no longer required at all. Britain built the rooms. Engineers found the signal. The market changed the rules. Every week, we tell the stories of what happened when those forces collided. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, a distinct problem, and a small workshop in Southfields, London in 1920. Before 1920, the wireless was not a domestic habit. It was a maritime necessity, a military tool, and a chaotic experiment. If a British household wanted to hear early broadcast experiments, they could not simply push a button on a wooden cabinet and fill the sitting room with sound. They had to wrestle with a crystal set. A crystal set, an early, unamplified radio receiver that relied on a piece of crystalline mineral to extract a signal, was not a shared experience. It was a solitary pursuit. It required a listener to wear heavy, uncomfortable headphones. It required a steady hand to adjust a fine piece of wire, known as a cat's whisker, against a rough crystal to find a faint, drifting signal. There was no volume control. There was no loudspeaker. The sound was a whisper pulled directly from the aerial wire. If someone bumped the table, the crystal shifted, the signal vanished, and the whisper was lost in static. What British listeners lacked was reliability, volume, and ease. They needed a way to amplify the weak radio waves traveling through the damp British air, to turn a faint vibration in a headphone into a voice that could comfortably reach the corners of a room. In Southfields, London, in 1920, Captain Stanley R. Mullard decided to solve this exact reception problem. Mullard was an engineer who understood the fragile mathematics of a vacuum. During the First World War, he had worked extensively for the Admiralty, developing high-power transmitting valves for naval communications. He understood how to shape glass, how to extract air, and how to control the invisible flow of electrons. When the war ended, Mullard saw that the future of wireless was no longer confined to dreadnoughts and military signaling. The public wanted to listen. He founded the Mullard Radio Valve Company to build the components that would make domestic listening possible. To do this, he had to perfect the valve. A valve, a glass electronic device used to control and amplify signals before transistors replaced it, was the absolute engine of early radio. Inside its evacuated glass envelope, a heated filament released electrons, which were then manipulated by a metal grid to take a microscopic radio signal and magnify it exponentially. Without a valve, the loudspeaker was silent. With a valve, the sitting room became a theater. Mullard's first major British entry into the consumer market arrived in 1921. It was called the Aura valve. The name was an acronym for exactly what it did: oscillates, rectifies, amplifies. It was a dark, pear-shaped glass bulb with 4 pins protruding from its base. It was not a cheap consumer good. In 1921, An ORA valve cost 15 shillings. In a period when an ordinary British labourer might earn just £2 or £3 a week, 15 shillings was a massive investment. It was equivalent to several days of hard physical labour. But for the early wireless enthusiast, the price was justified. The ORA worked. It was robust, it was consistent, and it did not burn out as quickly as its fragile competitors. Then, the British radio market exploded. In late 1922, the British Broadcasting Company began daily transmissions from London. Suddenly, the chaotic experiments in the ether became an organized daily schedule. The public wanted to hear the news. They wanted to hear the music from Savoy Hill. The crystal set was no longer enough. Households wanted a proper wireless set with a loudspeaker, and that required valves. The demand for the ORA valve and its subsequent variations immediately outstripped supply. The small workshop in Southfields could not cope with the sheer volume of orders arriving by post. Captain Mullard needed industrial scale. Available reports indicate that by 1924, the Mullard Radio Valve Company was producing an astonishing 2.5 million valves a year. To achieve this, the company abandoned Southfields and moved into a massive new manufacturing facility in Balham, South London. The High Street began to take notice. Local electrical dealers, who had previously sold lighting fixtures and bicycle parts, began stocking Mullard's distinctive blue and gold cartons. Magazines like Practical Wireless and Wireless World filled their pages with advertisements praising the British engineering inside the glass. A national component culture was born. If an amateur wanted to build a reliable receiver, the blueprints almost always specified a Mullard valve. The room did not care about the brochure. The signal did not care about the badge. The set either found the voice in the air, or it did not. And in the 1920s, a Mullard valve found the voice. The success of the ORA valve proved that Britain wanted to listen, but the early 1920s wireless market was still fundamentally constrained by the limitations of basic amplification. Early triode valves, simple glass tubes containing just 3 internal electrical elements, were inefficient. To achieve a volume loud enough to fill a British sitting room without using headphones, a radio manufacturer had to string multiple triode valves together in a single circuit. This made the wireless set extremely expensive to build, hungry for battery power, and highly prone to component failure. Captain Mullard possessed the engineering vision to solve this, but scaling up production required immense capital. In 1927, to secure financial stability, advanced research facilities, and crucial European patent access, the Mullard Radio Valve Company entered into a strategic partnership with the Dutch electronics giant N.V. Philips. It was not a surrender of British engineering. It was an industrial unlocking. This alliance allowed Mullard to introduce a revolutionary new component to the British market in 1928, the pentode valve. The pentode, a highly advanced 5-electrode glass vacuum tube that added extra internal wire grids to control the chaotic bouncing of electrons, was vastly more efficient at amplifying sound than any previous design. It changed the fundamental architecture of the British wireless set. Before the pentode, a radio receiver required 4, 5, or even 6 expensive valves to drive a loudspeaker. With the pentode, a manufacturer could achieve the same room-filling volume with just 2 or 3. The economic consequence for the British listener was immediate and profound. Because the radio cabinet required fewer internal components, less complex wiring, and a smaller power supply, the total manufacturing cost plummeted. The purchase price of a complete family radio dropped from the realm of luxury goods into the budget of the ordinary middle-class and working-class household. Simultaneously, It accelerated the shift toward the mains radio, a radio designed to plug directly into the domestic wall socket, finally freeing the British family from the dangerous, messy, and cumbersome acid accumulators that previous battery sets demanded. Describe a Mullard valve of this breakthrough era, and you describe the absolute scent and texture of early radio. It was a delicate glass dome, heavily silvered on the inside by a chemical getter designed to absorb stray gases. It sat firmly on a dark bakelite base, with stiff brass pins protruding from the bottom to lock into the receiver's chassis. When the set was switched on, it did not produce sound immediately. The listener had to wait. The internal heater filament had to reach operating temperature, glowing a dull, comforting orange through the silvered glass. As the valve warmed, the heat rose through the wooden cabinet, releasing the distinctive, unforgettable smell of hot dust, melting wax, and warm bakelite into the room. With this single component, Mullard established a formidable British radio moat. A moat in manufacturing is a defensive barrier against competitors, and Mullard's was absolute. If a major British radio manufacturer, such as Bush Radio, EKCO, or Murphy Radio, wanted to build a modern, affordable, high-performance receiver in Southend-on-Sea or Welwyn Garden City, they almost invariably designed their circuits around Mullard valves. The set makers trusted the consistency of the Blackburn and Mitcham production lines. The BBC engineering department trusted Mullard transmitting valves to push the signal out from the Daventry transmitter. But the true genius of the Mullard empire was not just securing the factory contracts, it was capturing the British high street. A valve was a consumable item. Like a light bulb, it had a finite lifespan. After a few thousand hours of heating, glowing, and amplifying the home service or the light program, the internal filament would eventually burn out or lose its emission. The radio would fall silent. When this happened, the listener did not buy a new radio. They took the faulty valve, or the entire heavy wooden cabinet, down to the local high street electrical shop. These independent radio dealers, who had previously been bicycle mechanics or lighting merchants, became the vital service network of the British Wireless. Mullard supported this high street ecosystem relentlessly. They provided shopkeepers with illuminated window displays, massive technical data books, and the famous Mullard Magic promotional literature. When an amateur enthusiast read Practical Wireless to build their own set, the blueprints demanded Mullard. When a local repairman diagnosed a dead set on his wooden service bench, he reached into a cardboard carton to extract a fresh Mullard pentode. The company had successfully positioned itself at every point of the listening journey. They supplied the transmitter that sent the signal. They supplied the factory that built the cabinet. They supplied the local shop that fixed the set. Every dial, every room, every voice. By the early 1930s, to look inside a British radio was to look at a Mullard product. The badge on the dial was not decoration. It was a promise about reception. Chelmsford built the idea. Droitwich carried the signal. Broadcasting House gave it a voice. The High Street sold the set. The kitchen made it ordinary. Britain made it a habit. By the late 1930s, the Mullard Radio Valve Company was no longer just a component manufacturer. It was the absolute industrial foundation of the British listening experience. To understand the scale of this dominance, one must look at the geography of production. The original Balham factory had been outgrown. In its place, Mullard constructed a sprawling, state-of-the-art manufacturing complex at Mitcham in Surrey. By 1939, the Mitcham facility was producing tens of millions of valves annually. But the outbreak of the Second World War changed the nature of British wireless production overnight. A valve was no longer just a domestic luxury For hearing the BBC national program, it was a critical military asset. The Mitcham plant began churning out specialized valves for radar systems, bomber aircraft communications, and the wartime civilian receiver. The austere, standardized utility radio Britain built under severe material constraint to ensure households could still hear government broadcasts. Because Mitcham was located in the south, it was highly vulnerable to the Luftwaffe's bombing raids. The British government and Phillips executives knew that if Mitcham fell, the military communications supply chain would collapse. To protect this vital production, a massive new shadow factory was commissioned in the north of England, far from the primary target zones. They chose the Lancashire industrial town of Blackburn. Blackburn was historically a cotton-weaving town, but its damp climate and highly skilled, adaptable workforce made it ideal for the delicate assembly of electronics. What began as a wartime contingency quickly became the jewel in the Mullard empire. By the 1950s, the British listening ecosystem was almost entirely dependent on what happened inside the gates of the Blackburn and Mitcham plants. The Blackburn site alone eventually expanded to cover 45 acres. It employed over 6,000 local workers, the vast majority of whom were women, prized for the immense manual dexterity required to thread microscopic wires inside glass tubes. The operation was a masterpiece of vertical integration. The factory did not merely import parts and assemble them. They manufactured the components from scratch. They mixed the raw silica and baked their own glass tubing. They smelted the metals. They drew their own tungsten wire, a resilient metal thread thinner than a human hair, used to create the internal heating filament that glows hot and releases electrons. This colossal industrial effort fed a national network of sound. When a British family tuned into the home service in a post-war kitchen or the light program in a suburban sitting room, they were relying on Blackburn glass and Mitcham engineering. The Mullard distribution network reached into every corner of the country. High-street electrical retailers, department stores, and rental chains like Radio Rentals and Rediffusion depended on a constant supply of replacement valves to keep their leased sets operational. Magazines like Wireless World and Practical Wireless published circuit diagrams that treated Mullard components as the undisputed standard. But the most visible symbol of Mullard's cultural dominance was not found in the factory. It was found on the counter of the local radio shop. In the 1950s, the company introduced the Mullard high-speed valve tester. A valve tester, a heavy, mechanical diagnostic machine that uses punched cards to instantly configure testing circuits for any specific valve model, was a revolution for the high street. Before this machine, diagnosing a faulty radio required a skilled engineer with complex meters. With the high-speed tester, a shop assistant at Curry's or an independent local dealer could take a customer's cold, dead valve, place it in the machine's socket, pull a lever, and read a simple dial: pass or fail. If it failed, the customer bought a fresh Mullard replacement from the carton on the shelf. The radio went back to the sitting room. The voices returned. The ecosystem sustained itself. To understand the absolute ubiquity of the Mullard empire at its zenith, one only had to look at a Bush DAC 90A sitting on a British sideboard in the mid-1950s. The DAX 90A was arguably the most popular mains radio of its era, housed in a sweeping, Art Deco-inspired brown bakelite cabinet. But the radio's famous reliability had very little to do with the Bush badge on the front. Inside the chassis, the radio relied entirely on a specific suite of Mullard components, known affectionately by engineers as the U-series valves. When a listener in a post-war sitting room reached out and turned the volume knob, they initiated a physical, thermal process. The electrical mains current entered the set and passed through a Mullard UY41 rectifier valve. The heater filaments inside the glass envelopes began to glow with a deep, comforting orange light. As the internal temperature of the cabinet rose, it warmed the surrounding dust, the cotton-covered wiring, and the phenolic resin of the bakelite shell, releasing that unmistakable, dry, warm scent of mid-century British electronics. The tuning dial, illuminated by a small pilot bulb, became a window to the world. A Mullard UKH-42 frequency changer valve took the invisible radio waves transmitted from Droitwich and converted them into a signal the radio could process. Finally, a Mullard UL-41 output valve drove the loudspeaker, pushing the home service out into the room. The radio was Bush, but the voice was Mullard. This dominance was not accidental, it was engineered. Beyond the massive production lines in Lancashire and London, the company had established the Mullard Research Laboratories in Redhill, Surrey. Here, hundreds of British scientists and technicians worked to push the boundaries of vacuum technology. They were not merely building components for the present. They were defining the parameters for the future of British broadcasting. As the 1950s progressed, the listening habit was joined by the viewing habit. Mullard aggressively expanded its Blackburn operations to manufacture cathode ray tubes, the massive, heavy, funnel-shaped glass vacuum tubes that formed the screens of early television sets. Just as they had monopolized the radio chassis, Mullard rapidly became the indispensable supplier for the booming British television industry. Whether a family bought a Pi, an EKCO, a Murphy, or a Kosser television from their high street dealer, they were almost certainly staring at a piece of Blackburn glass. To solidify this monopoly, the company launched one of the most successful technical advertising campaigns in British history. They called it Mullard Magic. They marketed their components under the slogan, "The Master Valve." Advertisements featuring the Mullard logo appeared endlessly in the Radio Times, Practical Wireless, and local newspaper classifieds. The strategy was brilliant. Mullard bypassed the radio manufacturers and spoke directly to the British public. They convinced the listener that a radio was only as good as the valves inside it. If a set lost its volume, or a television lost its picture, the customer was trained to walk into a radio shop and explicitly ask the repairman for a Mullard replacement. By the dawn of the 1960s, the ecosystem was entirely self-sustaining. The laboratories in Redhill designed the circuits. The furnaces in Blackburn baked the glass. The factory floors in Mitcham assembled the valves. The BBC transmitted the signal. The high street shops sold the cabinets. The local repairmen tested the components. The British public listened to the results. It was a closed loop of industrial confidence, high street commerce, and domestic ritual. The company employed over 100,000 people across its various European and British operations under the Philips umbrella. The factories ran day and night. The ledgers recorded millions of pounds in profit. The brand seemed entirely untouchable. But in the laboratories of competing nations, a small, cold piece of silicon was about to break the glass. The decline of the Mullard empire was not caused by a failure of engineering. It was not caused by a sudden drop in the quality of Blackburn glass, nor by a lack of affection from the British public. It was dismantled, systematically and irreversibly, by the structural forces of the British radio market. The turning point arrived not with a crash, but with a tiny, cold piece of germanium. In the late 1950s, the British wireless industry collided with Force 5, technological, retail, and listening culture shift. For 4 decades, the entire architecture of domestic broadcasting had been built around the vacuum tube. But physicists at Bell Laboratories in America had invented something that rendered the glass envelope completely unnecessary. It was the transistor. A transistor, a microscopic solid-state electronic component that amplifies or switches electrical signals by moving electrons through a semiconductor block rather than through a heated vacuum, did not glow. It did not require a highly trained glassblower. It did not take several minutes to warm up before the BBC could be heard. And most importantly, for the British radio listener, it drew a mere fraction of the battery power required by a traditional valve. At first, Mullard did not ignore this threat. They were a company of brilliant scientists, not simply glassmakers. As early as 1956, Mullard opened a massive state-of-the-art semiconductor manufacturing facility in Southampton. They attempted to secure the same absolute monopoly in transistors that they had held in valves. Early British transistor radios, like the pioneering models from Roberts Radio and Bush, proudly used Mullard's OC series transistors, which were sealed inside distinctive little black glass tubes. But the transistor fundamentally triggered Force 1, British cabinet, valve, transistor, component, labor and manufacturing costs. The economics of the valve were rooted in heavy, skilled British labor. At the Blackburn plant, thousands of workers were paid to mix chemicals, draw tungsten wire, assemble microscopic metal grids by hand with tweezers, and seal glass under extreme heat. It was an artisan process scaled up to a massive industrial level. A printed circuit board, a flat, copper-tracked board where electronic components are soldered directly into place, changed the mathematics of manufacturing forever. Transistors and their associated miniature components could eventually be mass-produced, printed, and soldered by automated machinery for pennies. The immense, highly skilled British workforce that had built the Mullard empire, the very people who made the brand a guarantee of quality, suddenly became a massive financial liability in a market obsessed with cost reduction. Simultaneously, the nature of British listening was fracturing. The family no longer gathered exclusively around a heavy, polished wooden radiogram in the sitting room to hear the home service. The teenage listener wanted to hear Radio Luxembourg under the bed covers. Families wanted to take the light program into the garden, on a picnic, or into the holiday caravan. They demanded lightweight portable radios. A portable valve radio required heavy, expensive, high-voltage batteries that drained quickly and cost a small fortune to replace. A transistor portable could run for months on a cheap, low-voltage dry cell battery. As the British public rushed to buy these small, plastic-cased portable sets, the demand for the heavy glass valves that Blackburn produced began to stall. The absolute dependency between the British radio cabinet and the Mullard glass furnace was breaking. The transistor opened the door to the next structural threat: Force 4, imports, private labels, and good enough listening. By the early 1960s, the British high street was flooded with a wave of imported transistor radios from Japan and Hong Kong. Brands like Sony, Sanyo, and Roberts' Far Eastern competitors produced radios that were smaller, cheaper, and remarkably reliable. Crucially, these imported sets did not use Mullard components. They used cheaper silicon and germanium semiconductors manufactured in Asia. The British radio moat had been breached. The listener did not care where the internal components were made, so long as the radio caught the pirate stations broadcasting from the North Sea. This technological shift systematically destroyed Force 3, high street retail, rental chains, catalogs, and online price pressure. For 40 years, the Mullard business model had relied on the repair economy. Valves were consumable items. Like light bulbs, they burned out. A single radio might require 3 or 4 replacement valves over its lifetime, generating a continuous, lucrative revenue stream for both the factory and the local high street dealer. Transistors, generally, did not burn out. They were solid, cold, and effectively permanent unless subjected to severe electrical faults. When a transistor radio did break, it was often cheaper for the consumer to throw the plastic set in the bin and buy a new one from a catalog than it was to pay an engineer to diagnose a microscopic fault on a printed circuit board. The Mullard high-speed valve tester, once the most profitable tool on the high street repair counter, was pushed to the back of the shop covered in a dust sheet, and eventually thrown into the skip. The independent service engineers, the men in brown coats who had diagnosed faults and sold millions of blue and gold cartons, saw their trade evaporate. The consumable market died. Mullard survived the 1960s and early 1970s primarily because of the television market. While radios had gone solid state, color televisions still required massive, highly complex cathode ray tubes, and Blackburn pivoted to produce them in millions. But by the late 1970s, even televisions became fully solid state, and the global manufacturing of display tubes shifted to cheaper Asian markets. The parent company, Philips, began a ruthless corporate consolidation. The name Mullard was seen as a relic of a bygone era, an old-fashioned British badge in a new globalized marketplace. Philips began to gradually phase out the Mullard brand in favor of their own corporate identity. The retreat was agonizingly slow, then painfully sudden. The Southampton semiconductor plant was absorbed into the wider Philips network. The sprawling Mitcham factory, which had once built the radar valves that protected Britain, was marked for closure. And in Blackburn, the jewel of the empire, the glass furnaces that had burned continuously for decades were allowed to cool. Thousands of highly skilled Lancashire workers were laid off. The machines that drew the tungsten wire were dismantled. The glass-blowing equipment was sold for scrap. A national infrastructure of listening was disassembled and shipped away. The repair counter closed. The service manual was discarded. The catalog dropped the valves. The high street moved on. The factory fell silent. The brand was diluted. The dial stopped glowing. The transistor answered instead. Today, the name Mullard has not entirely vanished from the earth, but its survival is a complicated ghost story of globalized electronics. In the decades following the Blackburn closures, the original brand was entirely absorbed and then discarded by its parent company. But a strange thing happened in the late 20th century. While the domestic radio and television markets had permanently embraced the silicon microchip, a highly lucrative niche market refused to let the glass envelope die. High-end audiophiles and professional electric guitarists still believed that a valve, specifically a vacuum tube amplifier, produced a warmer, richer, more musically pleasing harmonic distortion than any solid-state transistor could ever replicate. Because of this stubborn acoustic demand, the Mullard brand was eventually resurrected. The rights to the famous name and the distinctive shield logo were acquired by the New Sensor Corporation, an American audio company. Today, you can easily buy a brand-new Mullard valve. However, it is not made by highly skilled women in Lancashire. It is manufactured in a massive industrial facility in Saratov, Russia. The badge has survived, but the original British engineering bloodline, the specific chemical recipes for the cathode coatings, the proprietary Blackburn glass, the Mitcham tungsten wire, is absolutely dead. It is a licensed memory, printed on a foreign product, to evoke a trust that was earned half a century ago. Yet, within the British preservation and enthusiast community, the genuine article is hoarded like industrial gold. On eBay, on Facebook Marketplace, and at the swap meets of the British Vintage Wireless Society, the original valves manufactured in the 1950s and 1960s command a fierce and escalating premium. The ultimate prize for a vintage restorer or a modern audio purist is what the community calls new old stock, an original Blackburn or Mitcham valve that has been sitting untouched in its distinctive blue and gold cardboard carton for 60 years, never plugged in, its internal vacuum pristine, waiting for a heater voltage that never arrived. In sheds, spare bedrooms, and garage workshops across Britain, a dedicated army of amateur engineers with soldering irons and circuit diagrams from old copies of Practical Wireless, are keeping the Mullard legacy alive. They are carefully replacing dried-out wax paper capacitors, rewiring perished rubber mains cables, and testing old pentodes on restored Mullard high-speed valve testers. When they bring a dead Bush DAC 90A or a Murphy A40 back to life, they are preserving a very specific piece of domestic architecture. This is because the original still matters, and it matters for a deeply functional reason. A modern smart speaker is a black box of disposable convenience. It either connects to the internet router, or it is a useless brick of plastic. An old British valve radio, by contrast, is an open, repairable, physical agreement between the listener and the ether. An old British radio with a repaired capacitor, a cleaned dial, and a speaker still moving air can do something a smart speaker often cannot: make listening feel attached to a place. Not because it is old, because the act of tuning still asks the listener to meet the signal halfway. If you travel to the physical site of the Blackburn plant today, there is very little left to suggest that this was once the beating heart of the British wireless empire. The colossal glass-making machinery, the enormous chimney stacks, and the endless rows of assembly benches are gone. The 45-acre site is now largely a generic industrial park and business center, housing logistics firms and light manufacturing. The thousands of skilled workers who once drew tungsten wire thinner than a human hair have retired or passed away. The physical footprint of this colossal British empire has been wiped almost entirely clean from the Lancashire landscape. But there is a surprise footnote in the history of British radio, one that proves that an engineering empire can outlive its own factories. In 1954, the engineers at the Mullard Research Laboratories in Surrey published a technical document outlining a reference circuit for a high-fidelity audio amplifier. It was called the Mullard 5-to-10 circuit, designed simply as a promotional tool to encourage British manufacturers to buy a specific set of 5 Mullard valves. That circuit was so perfectly calculated, so inherently stable, and so beautifully balanced in its sound reproduction that it became the absolute gold standard for audio amplification. Today, deep inside many modern, boutique high-end audio amplifiers costing thousands of pounds, the circuit architecture is still fundamentally based on the mathematics published by Mullard in 1954. The company disappeared, but its mathematics outlived it. What this story reveals is the vast, quiet gap between what Britain says it values and what the British consumer market actually rewards. We praise the concepts of trust, repairability, local employment, and honest, built-to-last engineering, yet we consistently hand our money to disposable convenience, imported private labels, and unrepairable digital platforms. Mullard did not fail because it made a bad product. It disappeared because the British retail economy decided that a permanent, repairable radio component was an inefficient way to make a profit. But somewhere, in a quiet room, an old valve is still warming up. It is a Bush DAC 90A on a wooden sideboard, its internal glass heating up, smelling faintly of dust and time, still sitting in a British sitting room, its dial glowing warmly, its grill cloth vibrating slightly, waiting for a hand to turn the bakelite knob and find one more voice in the air. See you in the next video.